Now it is your turn to write some code. In these labs, you will build and test the array operations from this chapter in C. This is Lab 1. It takes about 25 minutes. Your goal is to write the shifting operations against a fixed size buffer and keep the elements packed together and in order. You will write two functions in C. The first is array insert. It puts the value v at index I, and it needs one free slot, so n must be less than the capacity. The second is array delete. It removes the element at index I. Both functions return the new length. To test them, start with the array 10, 20, 30, 40. Insert the value 15 at index 1. You should get 10, 15, 20, 30, 40. Then delete index 0, and you should get 15, 20, 30, 40. This is a hint. To insert, copy the elements from back to front so you do not overwrite a value before it moves. To delete, copy from front to back to close the gap. Before you run your code, predict which way each loop must go and why. Let us look at one solution. This slide is insert. Try your own version first, then compare it with this one, line by line. This is array insert. Look at the loop. It starts j at n and counts down while j is greater than IVIS copies from back to front. Each element moves one slot to the right. Because we start at the back, nothing is overwritten before it is moved. After the loop, there is an empty hole at index. We drop the new value v into it. Then we return n plus 1, the new length. Now the other half of the lab, array delete. Again, try your own version first, then compare. Look at array delete. Its loop goes the other way, from front to back. It starts j at I and copies a at index j plus 1 into a at index j. This closes the gap left by the removed element. Then we return n minus 1. The loop direction is the whole trick. Always copy away from the hole. That way, no live value is overwritten before it moves. Insert costs big O of n minus I, and delete costs about the same. Both are big O of n in the worst case, near the front, and cheap only near the end. This is Lab 2. It takes about 25 minutes. The goal is to make the speed gap between big O of n and big O of log n real by counting probes on the same sorted array. A probe means one look at the array. Linear search examines one slot per probe. Binary search tests one midpoint per probe. So the number of probes tells you exactly how much work each search did. You will write two functions in C over a sorted array of 16 integers, linear count and binary count. Each one returns the index it found, or -1, and adds each probe it makes to a counter. Run them for several keys and include one key that is not in the array. Predict before you run. For 16 elements, how many probes should binary search need in the worst case? About log base 2 of 16, which is 4 of 5. And which key makes linear search do the most work? Let us look at the solution. This slide is linear count. Try your own version first, then compare. This is linear count. It walks the array from the first slot to the last, one slot at a time. On each step it adds 1 to the probe counter, then checks if this slot holds the key. So its probe count is just how far it had to walk. Now the other half, binary count. Again, try your own version first, then compare. This is binary count. It keeps two markers, low and high, for the part of the array still in play. On each turn it looks at the middle slot, adds 1 to the probe counter, and compares that middle value with the key. If the middle value is too small, it moves low up past the middle. If it is too big, it moves high down below the middle. So each probe throws away half of what is left. That is why it needs only about log n probes. Now let us run both counts on the same sorted array for 4 different keys and compare the number of probes. Look at the results. For the absent key 100, linear search makes all 16 probes, but binary search still makes only 5. Linear cost tracks the key's position in the array. Binary cost stays near log base 2 of 16, no matter where the key is. This is Lab 3. It takes about 30 minutes. Your goal is to compact an array in place. You keep only the first time each value appears, and you keep the original order. You will write one function in C called remove duplicates. It takes the array and its length, and it returns the new length. The unique values should be packed into the front of the array in first seen order. This is a test. The input is 4247297419. The output should be 42791 with a new length of 5. This is a hint. Use 2 cursors. A read cursor walks over all the elements. A write cursor points to the next free slot for a unique value. We only have arrays so far, no hash set until chapter 13. So the natural answer is big O of n squared. Each new value is checked against the values you already kept. Do not forget the easy cases, all distinct and all the same. Let us look at the solution. Try your own version first, then compare. We start the right cursor, W, at 0. It points to the next free slot for a unique value. Everything before W is already packed and unique. The read cursor, R, walks over every element in turn. For each one we ask a simple question. Have we kept this value already? To answer that, this inner loop scans the values we have already kept, from index 0 up to the right cursor. If it finds a match, it marks the value as seen and stops. If the value was not seen before, we copy it into the slot at the right cursor, then move the right cursor forward 1. So the first time each value appears, we keep it, and we pack it toward the front. Each new value scans all the kept values, so in the worst case, when everything is distinct, the work is 1 plus 2 plus 3, and so on. That is big O of n squared. A hash set in chapter 13 would make each membership test big O of 1, and the whole routine big O of n. That is a preview of why we build more structures.